This lecture is to explain the marble down a ramp lab. We have a quote from Usain Bolt says, "I think my acceleration is very good and that's key for me." You may know that Usain Bolt was the person who's won the 100-meter dash the last 2 years or the last two Olympics. So, in this presentation, we want you to be able to determine the acceleration from a velocity versus time graph and determine the change in position from a velocity versus time graph. And from those, we want you to be able to use the equation that we have here that says A equals Vf minus Vi over T. Now generally these F's are subscripts and this I is a subscript, indicating that it is a velocity. It's not a variable on its own. So this actually stands for final velocity, and this stands for initial velocity. Alright, so the first variable we want to look at is time. We've looked at time before. Time is the interval between events. It's measured with either a stopwatch or a photo gate, and it's nearly always the independent variable because you can't change time as a result of some other variable. So we've talked about time before, and that's kind of a rehash. But now we want to talk about velocity. Now we did measure velocity in the investigation, and what we did is we actually measured the velocity at two different points. And how we did that is we used two different photo gates. So we used photo gate A, and what we did is we had this thing hooked up to this timer right here when the A light was on. And what we did is we said, okay, we want to know how fast it's going right there. Now, we call this the initial velocity. It's kind of an average, but it works pretty good for what we're trying to do. You take the diameter of the object that breaks the laser, because remember, a photogate works by having a laser that comes across. Whenever you break that laser, that starts the timer, and when the laser is allowed to reform, that stops the timer. So we can actually calculate the initial velocity as the diameter of the marble or whatever broke the laser divided by that time. And we can do the same thing at a second point, saying, okay, now that we have that, we can say, what's the velocity here? And in the first lab, we saw that the velocity was the same between 2 points. But in this lab, what we're looking at is as we move down the ramp, the velocity definitely changes. So, this velocity term, not only can velocity be kind of calculated by using distance over time, but can also be measured with a radar or LiDAR, which actually uses something called the Doppler effect, which we'll cover later this year. But the Doppler effect is how the radar or LiDAR work, and we'll talk about that when we talk about waves. Acceleration. So in the lab, we started to look at how velocity changes. The term acceleration actually refers to the rate of change in velocity. Now there's two ways that you can change velocity. Because velocity is a vector, you can either change its magnitude or you can change its direction. Those are the two distinct ways that you can change velocity. Well, since velocity, a change in velocity is acceleration, you can also say that acceleration has to be a vector as well. So because of that, acceleration requires both a magnitude and a direction. So in other words, it has to have a number, like let's say 5 meters per second squared, but then it also has to have a direction like east, or positive, or negative, or some sort of indication of what direction it's going. Now the SI units for acceleration are meters per second squared, and that makes sense with velocity being a rate of change in velocity. So examples of acceleration. Acceleration is kind of everywhere. So there's three ways where you can really accelerate in your car safely. The first one is you can push the gas pedal. Whenever you push the gas pedal, you have positive acceleration. So in other words, you have a car that's moving in this direction, and when you step on the gas pedal, you're going more in that direction. So because of that, when you step on the gas pedal, you're increasing your velocity in a positive direction. Therefore, you have positive acceleration. You can also do the same thing when you push the brake. When you push the brake, your velocity actually decreases. So in other words, your acceleration is directed opposite your motion, and you have a negative acceleration. The third way, both of these two ways affect the magnitude of the acceleration, or the magnitude of your velocity. But you can also affect the direction of your velocity. And when you affect the direction, that's by turning the wheel, by changing directions. Every time you change the direction the car is pointed, you've accelerated the car. So now if we want to compare velocity and acceleration, there are two distinct quantities, but they do have things that are similar. They are both vectors. They are both rates. In other words, they vary with time. And that's really where they stop. Okay, velocity is a measurement of how fast. Okay, whereas acceleration is the rate of changes, the change in how fast. You can have these things go in opposite directions. I could be moving to the right with an acceleration to the left. And you may think to yourself, how is that possible? Well, if you're going and you're slowing down, your change in velocity is backwards, even though you're still moving forwards. So really, that's all they have in common, is the fact that they're vectors and rates, but otherwise they're completely different things. This is v, this is a, this is measured in meters per second, this is measured in meters per second squared. They really don't have anything in common other than the fact they are vectors and rates. So from the investigation, we actually did this. We graphed the motion, and we actually did a graph of it to find the acceleration. And we said that the acceleration was the slope of a velocity versus time graph. So we said, okay, if you take meters per second, which is the rise, and you divide it by seconds, which is the run, you actually end up with meters per second, or meters per second squared. That right there is the unit of acceleration. So we know that the acceleration is the slope of a velocity versus time graph. Please do not get confused. A velocity versus time graph is different from a position versus time graph. A position versus time graph, the slope is the velocity. So it's very, very important that you pay attention. Also, the displacement from this is the area under the graph. So in other words, if you're trying to find the area of something like a triangle, if you were to find the area, that would actually be velocity times time. And when you multiply velocity times time, you actually get displacement, or change in position. So there's actually two different things you can find on a velocity versus time graph: acceleration and displacement. This is example A1. This is a car starts at negative 10 meters per second and moves according to the graph to the right. What is the final position of the car? So we're looking at position. Remember, where you are is where you started plus how far you've moved. Okay, so your final position is where you started plus your displacement. Well, if you look, I have a starting position of negative 10. And this is the most common mistake that people make on these, is they forget to account for the initial position. Then what you can do is you can add the displacement. I have a velocity versus time graph. So what that means is that the area under this line represents the displacement. So what I'm going to do is I'm going to draw this thing, and I'm going to put it in two different shapes that are easy to calculate the area for. It says, what is the final position of the car? So that means I can cut the graph down at 5 seconds. Then what I'm going to do is I'm going to draw this right here, and you can see that that clearly is a rectangle. You can find the area of a rectangle as base times height. Or in our specific instance, it's 5 times 5. So we can put a 25 here. But realize that's not the entire area of the graph. You can also say that you have a triangle right here, which is also under the graph. So you can find the area of that triangle. So in order to find the area of the triangle, it's 1/2 base times height, or 1/2 of 5 times 15, because it goes from 5 to 20, and that's the length of 15. When you do that, you get 37.5. And now you add those three numbers together. When you add those three numbers together, you end up with a total, or a final position, of 52.5 meters. This one says, what is the acceleration of the car shown to the right? So remember, we checked, we said we've got a velocity versus time graph. So we know that the slope is equal to the acceleration. So now we have to decide which 2 points to take. Since this is a straight line, it doesn't matter which of the points that I pick, because all the points on a straight line have the same slope. So the easiest ones for me to pick in this case are this one and this one. And the reason for that is they are both on corners of lines. They're easy points to read. For example, this first point is 0, 5. And the second point right here is 5, 20. Those are the easiest points to read. You could use these other points if you wanted to, but then you'd have to estimate and say, okay, well, I think that's going to be 18 or 16 or whatever. So it's easiest just to use the points that are the easiest ones to read. So now to find the slope, we do the change in y over the change in x. So 20 minus 5 over 5 minus 0. When we do that, we get 15 over 5, or 3 meters per second squared. This one says, what is the initial velocity of the car shown right? The correct answer is 5 meters per second, and you should be able to show that answer and explain it. Measuring acceleration. So now, in the lab, we didn't stop at just measuring the velocity of these two particular points. What we did is we said, okay, we measure the velocity at A, and we measure the velocity of B, and then we actually took a look and we divided it by the time that it took to go in between these gates. And we said that is how we can calculate the acceleration, which is basically the same thing as we did on the graph. On the graph, if you look, you have a velocity versus time. You have velocity and time. And what you're doing is you're picking 2 points, 2 velocities like we have here at A and B, and you're looking at the time that it takes to go between those. So what we did right here is the same thing as the graph itself. So you can measure acceleration directly if you need to. You can measure acceleration with something called an accelerometer. Accelerometers are designed to do this. A lot of them are liquid-based, but there are others that are microcontrollers. You can see accelerometers directly in Wiimotes, the Wiimote, the Wii U remote, PS3 controllers. You can see them in iPhones, iTouches, just about any tablet device now, and also in digital cameras, navigational devices. You'll see accelerometers in all those. Now you know there's an accelerometer in one of these because if you've ever tried to play one of the Wii games, you know that instead of actually swinging this controller all the way through, you can actually flick it really fast and you can have a much greater impact. The reason why is these controllers, they actually measure the acceleration, not how fast or how far the controller actually moves. So we get to the acceleration equation. And the acceleration equation is this one right here. It's A equals VF minus VI over T. Now it is very important that you realize if you're doing this in a calculator that you actually have to subtract these first. Now the parentheses are not on the formula chart, but it's something that you need to know to do. You have to subtract both of those first and then divide by the time. So we've already looked at these variables. We know A is acceleration. We know that VF is final velocity. We know that VI is initial velocity. And we know that T is time, or delta T is time. Now, you should be able to fill in the definitions for these based on the earlier parts of this lecture. You should also know that the SI units are meters per second squared, meters per second, and seconds. And you should be able to figure out how to measure each one of these as well. Stopwatch, accelerometers, and so forth. Alright, in this question it says a ball accelerates, and we want to look at the units. We say the units right there are meters per second squared, so that's going to give us an indication of what this is. Coming to 20 meters per second in 5 seconds. And then it says, what is the initial velocity of the ball? Okay, in this investigation, or in this question, we have an object that is accelerating. It's accelerating to the right at a value that is a positive acceleration. It's indicated by the positive 6.67. We know that it ends up with a final velocity of 20 meters per second. So it also ends up with a positive velocity. Okay? And we know that this whole process takes some time. So now we want to look at the information. We want to be able to calculate the initial velocity. So we're going to go ahead and take a look at the given information. We're actually going to take the numbers and assign them variables now. So we had the value of 6.67 meters per second squared. And what we want to do is we want to assign that a value. Because it's meters per second squared, we automatically know that's an acceleration. The next one we come to is 20 meters per second. Now, because it's in meters per second, we know right away that it's a velocity. But we don't know which velocity yet until we continue reading the question. It also tells us that we have 5 seconds, and 5 seconds has to be a time. So then we just have to decide if this is the initial or final velocity. There's two clues in this problem. It says it comes to 20 meters per second, indicating that it's the second velocity. And then if you continue along, it says what is the initial velocity. So you know that this must be the final velocity. Now we're trying to solve for the initial velocity. Now the principle that we're going to be using is actually something called if-that. And we're going to talk a little bit more about if-that later. But basically, this is a way of us being able to figure out which equation we're going to use later on when you learn a few more. So now that we know that, we know our formula. Our formula is involving acceleration, so we know the equation is A equals VF minus VI over T. So we look at our stuff to see if there's any irrelevant information. Is there anything extra? Well, we're trying to solve for VI. We have T, VF, and A, and all the variables are accounted for, and there's nothing left over in the given. So we don't have any extra information. So now we can go ahead and plug in our numbers. So we can say 6.67 equals our final velocity minus our initial velocity divided by our time. So now, this is a pretty easy one to solve. What we're going to do is we're going to take both sides and multiply it by 5. When we multiply both sides by 5, we're going to end up with 20 minus VI equals 33.535. And now we can go ahead and solve. So the easiest way to solve it at this point is to go ahead and subtract 20 from both sides. And when you do that, you're going to get a value of 13.35 equals negative VI. Now realize you're not trying to solve for negative VI, you're trying to solve for VI. So you actually need to divide both sides, or multiply, by negative 1. When you do that, that'll actually cancel out the negative there, and it'll leave you with the final answer. The initial velocity is negative 13.35 meters per second. People usually have a hard time with this. They say, well, wait a second. If you go back to the picture, I have an acceleration that's to the right, and I have a final velocity to the right. How can I possibly have an initial velocity to the left? Well, it just means that you started this way, and the acceleration took over, and it gradually made you go less and less and less that way until you actually changed directions and went the other way. Remember, the negative is just an indication of direction to begin with. This question says, determine how long in minutes it takes for a car to accelerate from rest to 30 meters per second at 0.1 meters per second squared. Now, I will tell you that the key there is solving the question and converting it to minutes. You should be able to get the correct answer of 5 minutes all on your own. We get to the last example. It says the car accelerates from 6 meters per second to 15 meters per second in 3 seconds. And you should be able to get the acceleration as 3 meters per second. And you should be able to do that entirely on your own.